All right, good afternoon. Can you hear me? How's the voice check?
Yes.
All right, great. Thank you very much. Okay, so welcome everyone to our next class on preclinical molecular imaging. So today the plan is to finalize our discussion on CT imaging. So today it will be more about the applications. So the last part of the of the lecture. If there will be some time left, so we'll start talking about the PET fundamentals. So we'll switch to another imaging modality, which is a positron emission tomography, which uses the radioisotopes for imaging. And then on Thursday, so we'll continue with the PET imaging, but also I would like to spend some time to discuss the homework. So we'll have the first homework, which will be focused on the image analysis of the CT images. I will give you the short presentation, what to expect, and give you a short training, what you will be using, what type of tools you will be using for to complete the assignment. So it will be a relatively easy assignment, but it requires some brief training. So without further ado, so let's start with the with our conclusion of the lecture. So let me just share my screen, and here we go. So last time, so we finished talking about iodinated contrast agents. So these are the contrast agents that they contain a lot of iodine. So in terms of the percentages, between 40 to 60 percentages, 40 to 60% of the iodine content. And why iodine? Well, because iodine has a lot of electrons on the outside shell. And those electrons are, they contribute to the very high attenuation of the X-rays. So therefore, very often those iodinated contrast agents, so they are used in imaging, CT imaging in patients. And why we use generally the contrast agent is to separate the intensity of the blood pool and the, let's say, tissue. Because without contrast agent, both the blood and the tissue will look exactly the same. So we cannot image or differentiate between the vessels and the tissues. So therefore, adding the contrast agents, in this case, iodinated contrast agents to blood pool, so by injection to the patient, so we can then see, for example, or differentiate the heart tissue from, let's say, the blood within the left ventricle. And why it's important, I will just show you in a moment. So we defined the advantages of those iodinated contrast agents. So one is that it's a very good contrast with a high attenuation ratio. It's FDA approved. It's used for clinical procedures for many years. However, the very distinct disadvantage of the contrast agent, iodinated contrast agent, is a dose-dependent nephrotoxicity. So it was found that the patients that they require a lot of injections for imaging, so they develop kidney failure. So therefore, it's considered as a major disadvantage. The other thing is that the iodinated contrast agents, those used in clinics, so they have a very short blood residence time. So very quickly after injection, so they disappear from the screen because they are washed out by the blood and filtered by kidneys and excreted through urine. So, which is good for clinical systems, but it's not good for preclinical imaging systems, because as you remember, or I can just remind you, that clinical systems, they have a very high temporal resolution, so in milliseconds, so you can acquire the images every several milliseconds. In case of preclinical imaging systems, it's in minutes. So to acquire one three-dimensional scan, it takes a couple minutes to complete. So therefore, after you inject very quickly, like a bolus injection of the ionated contrast agent, so within several seconds it will be gone. So if you are doing the preclinical study, so then you will not notice any change in the contrast between blood and the tissue. So what is the solution? Well, the solution is that about 10 or 15 years ago, I don't remember exact date, but it was introduced so-called the long residence time alternatives for imaging, for the contrast imaging. And these are kind of names which are called fenestra vascular contrast agent or liver contrast agent. And they are also iodinated, but they are, the iodine is encapsulated within the lipid spheres. So these are kind of like a nanoparticle imaging, which allow very slow clearance through the liver. So that's why the contrast stays in the blood for up to 4 hours. So it's a very good advantage because after injection of this contrast agent, it stays for several hours. It's not FDA approved, so it cannot be used in patients. However, it was found, it was successfully used also in my research groups to image to image this contrast using preclinical systems in experimental animals. Unfortunately, to get very good quality images, it requires relatively large volume to be injected. So therefore, it's become very expensive to image, for example, a single mouse. It costs about between $60 to $100 with the cost of the mouse, which is around $25, $30. So you can see that the contrast agent it's double the price of the single mouse. So these are the examples. So on the right side, on the top of the slide, so you can see this is this kind of like a nanoparticle or microsphere, lipid microsphere, which contains a lot of iodine as well, which provides the contrast. And because it's encapsulated with this kind of like a lipid sphere, so it's not cleared so quickly from the blood. So that's why it stays for a couple of hours. And the images are shown at the bottom. On the left side, you can see the fenestra vascular contrast agent, where we can, after injection, so we can see very nicely actually the delineation of the tissue or the left ventricle of the heart and the blood, which is much brighter because of the contrast. On the right side, it's a specific contrast agent. It's Fenestra LC for the liver imaging. So it's only binds to the liver. So therefore, you can use this, for example, to observe a liver tumor. So liver tumor is shown actually over here as this dark, kind of like a shadow on the image. So, and using this Fenestra VC, so we did some kind of interesting studies, and I would like to share it with you. So I don't know how much you know about the heart physiology, but or for example, at looking at something which is called ejection fraction. So ejection fraction is the diagnostic value of the percentage of the volume that is ejected from the heart. And this ejection fraction, it's expressed in percentages. So between 50 to 70% is considered normal. However, everything which is below 50 or in a range of 40 or so, it's considered that the heart doesn't work so efficiently. And in many physiology books, for example, for medical students, so this is this kind of very known diagram. It's called Wigger's diagram, which shows the relationship between the different pressures. So, for example, we got the arterial aortic pressures, which is shown in the black. Then we got the ventricular pressures, which is shown in the blue. We got ventricular volume, which changes over time, and then everything is overlapped on the signal from the ECG. So based on this, you can find out that the QRS peak, which comes from the electrocardiogram. So this is the beginning actually of the phase where where there is increase in the ventricular pressure, which is associated with the decrease in the volume, and then there is the next cycle and so on. So one of the way or the method that you can evaluate the ejection fraction. So you can, knowing, for example, the volumes of the heart from different type of imaging, you can calculate the stroke volume, and knowing the stroke volume, which is the difference between the end diastolic volume and systolic volume. So you can calculate the ejection fraction and express this in the percentage, so multiply by 100%. And then the cardiac output, so this is actually the volume that heart's outputs during each cardiac cycle. So it's the stroke volume multiplied by heart rate. So these are important parameters which they need to be measured using diagnostic tools. And what is typically done, so maybe let me show over here. This is done using the echocardiography. So this is the ultrasound-based method for imaging the heart. So it's it's a sonogram of the heart, and shown over here on the left side. So these are two-dimensional images of the 4 chambers. So this is a left ventricle over here. The right ventricle it's not shown very well. And these are actually 2 atria. One is the left on the right side. It's a left atria. On the left side is actually right atria. This is another kind of like a plane on the same heart. And on the right side, so this is a 3-dimensional image only of this very small fraction, which shows the valves, so the heart valves, how they work and so on. So the physicians, they can assess what's the quality of the valves, if they are completely closed during the cardiac cycle or they require replacement. And ultrasound imaging is actually used for assessing the function. Cardiac function as well. So these are the images taken from the rat heart. And let me just place a video. So play a video on the left side. So this is the video which shows a normal contraction of the heart, of the healthy heart, of the healthy rat. So you can see this is a left ventricle, which nicely kind of like compresses all the parts of the all the walls, they compress very nicely. However, after myocardial infarction, so after the heart attack, so the image looks a little bit different, right? So you can see that the heart doesn't contract so well. So there is still kind of like some dead volume, which is not ejected from the heart. And if you compare those two, for example, in terms of the ejection fraction values, so one, it will be in kind of like a normal range of about 50, 60, 70%. This one on the right side, which is after infarction, it will be less than 40%. So how we can measure this? Well, with the ultrasound, definitely we can do the ultrasound imaging. And calculate actually the volumes of the heart at different phases of the cardiac cycle. So how the heart beats, so then the diagnostic, the technician, the ultrasonographer measures actually the volumes and then calculates using the formula which I showed in the previous slide, calculates what is the ejection fraction, knowing what is the minimum and maximum volume of the heart. But what we wanted to do, we wanted to try if we can do this using the CT imaging. So these are the images taken using the dedicated micro CT image after injection. So this is done in mouse. So very, very tiny hearts you can see over here. After injection of the contrast agent, so after injection of the Fenestra VC. So we acquired those images, as you can see. So they are several of the slices. These are closer to the apex, which is on the left side. They are some on the in the medium kind of plane of the heart, and then closer to the base. And then we got something which is called long axis, so different type of the planes of the heart. But looking at those images, you can appreciate the quality, right? It's a much better quality, much nicer visualization if you compare to the ultrasound imaging. So we thought that because we can acquire those images using CT and so-called a gated CT, because we could precisely let the scanner know at what kind of like a cardiac cycle it needs to shoot the X-rays and collect the image. So the collection of all those images of the whole heart during the single cardiac cycle, it took us almost 60 minutes. So very long study actually. It took a lot of processing, but the quality are great. But the images are images, but how we can quantify that. And we use actually two group of, so it was in collaboration with another group on campus of Professor Nashkal Sotra from MCB. And he got actually two different strains of mice. So one, the control mouse, and the second, which was a knockout mouse who experienced the heart failure. So it was a spontaneous model of the heart failure. And so we've been using the CT imaging actually to acquire images and try to quantify the ejection fraction. So how we did this, so we acquired the images and then you need to contour all the images just to acquire or measure what is the volume of the heart. So we had to do multiple contours on different planes, looking at the left ventricle, and then interpolate actually interpolate those different regions of interest to create one three-dimensional volume. And we could calculate what is this volume at different phases of the cardiac cycle. So it took several hours actually to process those the data set. But what we found that and we looked this that because the CT images, they provide the information about ventricular volumes. So when we place them on the Weiger diagram, so we could almost fit the curve of the ventricular volume, right? So so there is almost a very close close approximation of the ventricular volume. Same with the control and with the treated animals. And using this method, so we've been able to calculate the ejection fraction in the control, but also in the experimental animals, which show that in fact in those knockout or treated animals, so the ejection fraction is much lower than in the controls. So that's one of the applications. Of course, most of the CT applications are focused on imaging anatomy. So looking at the broken bones, right? Looking at also the tumor growth. So you can definitely see the tumors growing in the lungs or in some areas that they provide some contrast difference between the tumor and the other tissues in the proximity. But I wanted now to switch to another experimental agents, which are barium bismuth based agents. Remember this in the previous lectures, I showed you the example of the fluoroscopy. So this is a two-dimensional method which uses the X-rays. And in this case, it allows for the dynamic imaging of some process. And it was shown a movie of the patient who is swallowing some contrast. And I mentioned to you that it's a barium sulfate contrast. It's an insoluble salt, and it provides a very high contrast. So those type of contrast agents, barium / bismuth based agents, which provide a very nice contrast, and for example, in vasculature, can be used to image, for example, atherosclerosis. So I'm sorry, the arteriogenesis, so formation of the vessels or the vascular tree in animals, not in the patients because it's a postmortem technique. So this is the example of an image on the right side. I think it's even a movie, which probably you will not. It's actually doesn't work. But we acquired this in the 3D. So this is the example of the emulsion. So barium sulfate with the bismuth sulfate with a mix of 70 to 30. And it was injected directly to the aorta, abdominal aorta, after fixation with the buffered formalin, and then we pressure filled the vasculature and acquired with a high resolution CT image. So you can appreciate actually that the vasculature is very clearly seen. It's much better than any other techniques. Unfortunately, one disadvantage is that it can be done only post-mortem and of course in animals. However, it's inexpensive and it's relatively easy to use. So you can buy barium, those sulfates at very low price. To prepare this, it's also very easy. However, it requires some surgical skills to inject inside the vasculature, but the images looks gorgeous. And because it's a post-mortem, I'm sorry, I'm just getting some screens here. Let me see. Let me just restart the sharing the slides, because I don't know what's happened. Can you see the slides again? Could you just let me know?
Yes. Okay,
great, thank you. So, and because it's a postmortem imaging only, so therefore the serial imaging is not possible. So you cannot inject the animal, acquires some images, and let's say after some therapy or therapeutic intervention, you would like to visualize if there are more vessels or maybe more dense network of the vessels and do the study again. So it's unfortunately, it's not possible because it's a postmortem technique. So all of those techniques, they have their own advantages, disadvantages. So it's really depending on the application that you want to do or the study that you plan to execute. So it's really the choice of the contrast agent is based on this kind of rationale. So let me just switch a little bit to another type of imaging or another kind of like a feature of the X-rays. So far we've been talking about in terms of the X-ray theory that it's associated. So the attenuation of the X-rays is associated with so-called linear attenuation coefficients. So different materials, they have different attenuation coefficients. So for example, like barium, which I showed before, so it was very high attenuation coefficient. The iodine has lower, but still significant attenuation coefficient. And on the right side, so this is the graph, which shows the energy. So this is the energy of the X-rays. And on the left side, this is the logarithmic scale of the linear attenuation coefficient of different materials. And you can observe, let's say, let's start with this very basic one. So this is the water. So water has some higher attenuation with the lower energy, but of course then when the energy increases, the attenuation decreases as well. So it tells you that water is actually not a good contrast agent for CT imaging. Then we have some of the elements, for example, iodine, barium. Hold on, there is some chat message. So is CT angiography and contrast enhanced CT the same thing? Yes, it's exactly the same thing with the exception that angiography, because the name says angio, it's associated with the vascular imaging. But you can, for example, do some other contrast enhanced CT, which will be not focused on vascular imaging. So angiography, CT angiography is a part of the contrast enhanced CT. Yes. So going back to this graph, so we have some elements, chemical elements, that they have those kind of interesting features that at some moment of the energy, so when the energy increases, so let's look at the iodine, right? So iodine is actually orange color over here. So when the energy reaches about 35 or close to the 40 kilo electron volts, so then there is a dramatic increase in the attenuation coefficient, linear attenuation coefficient. That it's dramatic if you look at, for example, at the logarithmic scale. So we are talking, several orders of magnitude higher. And the same is, for example, in the others. So gadolinium, same as with the barium, with the gold nanoparticles, or generally in gold, is the same thing. This is associated with it's so-called like a K-edge process. And this linear attenuation coefficient, so shown over here in the graph, so they are orders of magnitude greater than the soft tissue for the electrons, for the photons of 20 kiloelectronvolts to 120 kiloelectronvolts. And this is called the K-edge phenomenon, because this kind of sudden increase in the attenuation coefficient of photons is occurring because because the photon energy is above the binding energy of the K-shell electrons. This K-shell electron energy, binding energy, it's very specific for different chemical elements. So I am telling this because what we can do, we can actually do so-called a dual energy CT. So this is the kind of advancement or a new feature of the X-ray CT systems, which have been introduced not long ago. It's probably within last 10 years when it ended up to be used in the clinical imaging. So we can do images of the same material using two different energies. So one which will be before this kind of K-edge jump of the attenuation, and after. Why we want to do this? Well, because we can do something which is called a K-edge subtraction. So we scan at the lower and higher energy, and then because the attenuation in contrast region increases by about 10-fold above the K-edge, so it provides actually a very sensitive image of the contrast agent. And I have actually the example here. So this is the dual energy imaging of the patient, which was injected with the iodinated contrast agent. So this is the iodinated contrast agent. And now what we can see, that when we are imaging at two different energies, so we can see that the attenuation of the iodine at those different energies, it's actually larger in terms of the difference than in bones. So which means that actually we are getting much higher sensitivity of imaging using the iodine of vessels than the bones, which led to the idea that we can, from the image which contains both the iodine and also bone structures, so we can subtract one image from another. And then get a very nice actually image of the vasculature of the patient without bones, right? Which masks the image on the left side. So this is a technique which is used right now in clinics. Unfortunately, it requires the system which allows for the dual energy imaging. So very often those dual energy scanners, they have two dedicated X-ray tubes which operate at two different energies, and they acquire the same image at the same time. So, and why it's important? Well, because on the right side, for example, when the doctor sees the vascular tree within the legs, so he or she can observe that there is some blockage of the artery on the this is the left side of the patient. So which may lead to kind of ischemic leg or leading to some ulceration or maybe amputations if it will be not fixed, right? So so then based on this image, the doctors, they can diagnose that this is the occluded vessel, and it requires either the vascular catheter placed and maybe cleaned the occlusion over here, or placement of so-called bypass. So surgical implantation of the vessels which will bypass this occlusion and provide the blood and nutrients to the lower extremity. So this is the dual energy. So again, so what the other contrast agents are available? Well, I showed you this before, so let me just show one more time. When we are looking at the gold, so the gold is another contrast or element which has been successfully used as a contrast agent in the form of the gold nanoparticles. Because it has the KH at relatively high energy of about 80 kiloelectronvolts. So there are some commercially available particles. So these are nanoparticles, gold nanoparticles called Aura-Vist. So they are commercially available, and they have actually about 3 times higher absorption, which enable actually the higher contrast at lower X-ray dose and higher resolution. So it provides low viscosity. It's almost kind of like a viscous or similar to the iodine agents. Relatively low toxic. There is no nephrotoxicity associated. It has also longer blood residence time, as we can see over here. This was the data shown in the mouse blood that so starting from like a 30-35% of the percent of injected dose, so going about 50, it will be probably within 5 minutes or so, and it will stay for several other minutes in the circulation. Unfortunately, because it's a gold, so that's why it's very expensive, right? And it's not FDA approved, so it's for experimental. It's experimental contrast agent. But we tested this in the lab about 10 years ago. So on the left side, so you can see the samples of the saline, so just using the physiological salt solution. And on the right side, it's undiluted contrast agent, so those nanoparticles. As you can see, the contrast agent is beautiful. And then after injection of the contrast agent, the gold nanoparticles to the animal, so now you can see that it actually stays very well in the vasculature and the bloodstream, blood pool. So that's why you can image the heart, so showing the right ventricle, right atria, right ventricle, left ventricle and left atria with a very nice resolution. If you compare this to, for example, a non-contrast baseline imaging, so definitely we cannot see any features of the heart. So we also did this kind of effect of the X-ray energy. So when you increase the energy, right, of the X-rays, so in this case, there should be a drop of the intensity of the tissue because the higher energy X-rays are more penetrating. But because of this KH phenomenon, the contrast should be more visible. And I think maybe it's not very clear from those images, but we did some calculations, and it shows that when you increase the energy of the X-rays from 55 to 80 kilovolts, so then the tissue around, so which is not associated with the contrast imaging, so all the tissue which doesn't contain the gold nanoparticle contrast, it's kind of dimmer, right? And actually the intensity of the heart or the blood pool it's higher than normal. So the difference between the contrast allows for much nicer quality of the images again. Then we also tested blood residence time. I mentioned that within 5 minutes, it's about 50% retention of the contrast agent. So it's actually confirmed that after injection, so within a minute, so we can still see the contrast agent, but then after 10 minutes or even more, after 20 minutes, the contrast agent is completely washed out and ends within, or it's being retained by the bladder. So this is actually the contrast agent which has been filtered by kidneys and stays in the bladder. So several years ago, we had also this idea that why we are spending hundreds, thousands of dollars for buying a contrast, maybe what we can do, we can synthesize our own contrast agent. And I've been working with a friend of mine, a chemist at Yale University, about 10, 15 years ago, when we tried to synthesize our own multimodal agents. So in addition to imaging using the X-ray CT, the blood pool, so we wanted to do also imaging using one of the nuclear techniques, which we'll cover in the class later, single photon emission computed tomography, which will require that this contrast agent will be not only not only attenuating X-rays, but also will be radioactive. So this is actually what we planned to do. So this was our planning, that we'll use a nanoparticle, which is called a dendrimer nanoparticle. And this dendrimer nanoparticle can be functionalized with different kind of functions, almost like a Lego blocks, right? So if you have, for example, some kind of framework, so you can add additional blocks around, and kind of works similarly. So we added a compound which contains a lot of iodine. So this is a TIBA, so triiodobenzoic acid, which contains, I don't remember now out of my head, but it's probably around 50 to 60% of the iodine content, so very high iodine content. So we ornamented the nanoparticle with some of the TIBA, and we also added the complexing agent, so DTPA, complexing agent for radioactive isotope, which is a technetium-99m for SPECT imaging. Of course, we added also several other components just to increase the circulation time, because this was another requirement, that in addition to having this nanoparticle or imaging contrast used for two different imaging modalities, we wanted also to increase the circulation time. And and we completed the study. So we synthesized and characterized chemically that it's really this nanoparticle. We radiolabel it and performed several of the studies. So these are kind of like a summary of those studies. So first, we compared this to the iodinated contrast agents, so those which are used in clinics. And this is actually the name OmniPEG. So this is the GE Healthcare iodinated contrast agent. So we use 20% of the contrast agent compared to our agent in terms of the attenuation. And as you can see, it's pretty good, right? So with a high concentration, the intensity is comparable to the iodinated contrast agent. Then we also look at the calibration, attenuation calibration curves. So this was a concentration of the iodine, and this was our actually the intensity of the image. So for both actually compounds, we got some linear relationship between the concentration and the attenuation of the signal. And then we look at the circulation half-life. So in our case, this nanoparticle, which we synthesize, stayed at the level of 50% within 0.7 hours. So it was 45 minutes it stayed in the circulation. So it was well enough actually that you can perform several studies during this 45 minutes. Then we also compared or looked, because so it was a radioactive as well contrast agent. So we did also the biodistribution, so organ biodistribution, just to find out where this contrast agent goes. So after injection to the animal, and we observed that, well, it stays in the blood for some time, right? So it starts from 0.5 hours up to 6 hours, and it's still at around 5% of the injected dose. It's a pretty good one. And then most of the contrast agent is being excreted through urine because of the kidney filtration. So that's why we can call it that it is a predominant renal clearance and excretion. And these are the example of the images. So we took at the different time points from before injection, then during the injection, and then up to 90 minutes after injection. So these are different planes of the heart of the mouse. As you can see, the contrast agent stayed and produces very nice quality images up to 90 minutes, definitely, and probably more. But we didn't have a need for keeping it longer. So it was successful in terms of the attenuation, but also the increased residence time. And And this was a successful study. So we used this contrast agent for several other studies, including also SPECT imaging. I didn't show the SPECT images here because we'll be talking about the SPECT technology later in the semester, so I can show you the examples at that time. So finally, before we'll finalize the CT imaging, I wanted to tell you about several of the dedicated preclinical scanners for in vivo imaging. So one of the, I would say, first scanners which were dedicated for small animal imaging and contain only CT as a main modality, it was the GE Explorer CT120. So the system is shown on the right side. So inside you got the gantry, which rotates around the animal, which is placed actually over here. So as you can see, everything is shielded, right? So so they are shields which protect from the radiation. So the operator, for example, I've been operating this system for several years. So there was a minimum exposure of the X-rays to our body. So it provided a very high spatial resolution. The maximum that we could get, it was at the ballpark of 25 microns, up to 200 microns. Then what I really liked in the system, it was a relatively high temporal resolution. So remember when we've been talking about the clinical systems that they have a very high temporal resolution within a milliseconds, which means that because of the very high rotation of the gantry around the patient, so you can acquire practically every 10, 20 milliseconds an image. In case of the preclinical systems, because we don't have this very high speed rotation of the gantry around the animal, so it's a couple minutes. But this system allowed actually to increase the scanning up to 1 minute. So it allowed actually for dynamic micro CT images. Hold on, there is a question. The Elizabeth asked, can you please explain what the high end of the spatial resolution means? Well, so the lower end, so 25 microns, it's the smallest possible, right? So smallest possible resolution, which means that you can differentiate the two, let's say, vessels or objects which are separated 25 microns each other, but you can still recognize them as two distinct objects. The higher the higher spatial resolution of the 200 microns, it shows what is the poorest resolution, right? Because all those systems, they have their own protocols, right? Or parameters that you can change. And actually, if you are interested in very high acquisition, which will take, for example, quick time, but also it will not require a lot of data to acquire. So of course, there will be a compromise. So the compromise will be with the spatial resolution. So that's why if you try to acquire very quick scans, which will not take too much of your disk space, so that's why increasing or making it less, kind of like a poorer resolution. So 200 microns, it was the poorest resolution for this particular system. So all the systems, they have this kind of like two extremes. One, what is the best resolution that you can get? And the second is what is kind of like a lowest resolution, which allows you to save a time and also the space on the disk. So another kind of feature was that it had relatively high penetration energy. So typically preclinical scanners, they are up to 80 kiloelectronvolts, but in this case, the X-ray source, they provided between 70 to 120 kilovolts. So much higher energy of the X-rays allows for a better penetration of the specimen. It was also possible to do so-called the ECG and respiratory gating. We'll be talking about the ECG and respiratory gating during our discussion on the quantitative imaging later in the semester, so I will not cover this more right now. And then, of course, it allowed also, because it was produced by the GE Healthcare, so it allowed the interconnectivity with the kind of like a clinical, full-featured GE Advanced Workstation for image analysis. So, so we could take, for example, the images acquired in this preclinical scanner and take it actually to the hospital to do all type of kind of processing using the clinical image analysis workstations. So, hold on, I got another, here you go. So those type of scanners, they allow different type of imaging, so high resolution imaging. This is one which is, I call it the quantitative micro CT imaging. So this was the this was the study also with the surgeons where they implanted in the mouse. They took part of the abdominal aorta and exchanged it into an artificial vessel. So artificial vessel, which was grown on the, almost like a Petri dish, we can say it, or incubator. And they wanted to test it if the vessel is functional, which means that if the vessel is patent, so there's no blockage within this graft. So therefore they asked me to perform those kind of quantitative studies. And these are the example images. So the graft is actually shown over here. So this is pseudo-colored, right? It's not a real color, but I segmented out the graft and changed the color just to visualize it. But then you can also perform the quantitative imaging, which means that you can look at the graph in more kind of like in the more detail, and for example look at the line profile, which shows the diameter, right? So for example, we can see over here that in this particular graph, when it was sutured to the upper part of the abdominal aorta, so this was kind of like increase the diameter because it was bigger graft than the aorta. But then there was some kind of like a problem probably with the suturing in, which made it less patent, which means that the contrast was flowing through, but the diameter actually decreased, and then it was like a regular aorta. So you can do all those type of measurements. So in this particular measurement was about 2 millimeter diameter, so very small diameter. But with the high energy, but also high resolution scans, it's possible to do those analysis. But they are also systems which allow you to scan specimens with even lower resolution. So lower in terms of the you can go down to the single micrometer size, right? So ultra high resolution of the scanners. And these are kind of more dedicated for specimen imaging and post-mortem imaging. One of the examples that I work with, it was a GE Explore Locus SP. So this particular system allowed us to go down with the spatial resolution to 6.5 microns. Unfortunately, if you go lower with the resolution, so going to very small specimens, it increases the acquisition time and of course the space on your disk. So just to acquire the images that I will show you in the moment, it took us 4 hours of the imaging scan. So very long. The energy penetration was relatively high, so same like in the previous example, because it was also produced by GE Healthcare, so there was interconnectivity with those advanced workstations. And why those workstations or those advanced workstations, it was a benefit? Well, because those clinical systems and the software, which costs like $20,000, $30,000, which is a prohibitive cost for preclinical researchers like myself, for example. So therefore, using those kind of high-end workstations with a great software allowed us to create beautiful images, which I wanted to show you right now. So this was a mouse heart, so very tiny heart, as you know from the mouse. We took it, we perfused with a contrast agent, and then we acquired the images. So micro CT scan after acquisition show actually this type of image. So there is a hard surface and there are some vessels, but it's a lot of kind of like artifacts, right? So it requires really a lot of processing to get some information. but those advanced workstations, which we've been able to use, had actually those algorithms, very specific algorithms for cleaning out the image and producing some images that we can use for presentations or quantification. So Elizabeth says, why is the penetration energy so high if the mouse is so small? It's a very good question. Because definitely the penetration energy for a mouse, if you're talking about 120 kilovolt energy, which is used in clinics, for example, in patients, in human patients, so this energy is definitely high for mouse. High, but it doesn't mean that it's a bad thing. It means that there is a good penetration, so there is this really no kind of effects which are called the heart beam effects, which we'll be talking about later about this. Also, it allows for imaging not only mice, but also small specimen. I mentioned to you last time that, that at some moment I had a request from the Natural Museum History, Museum of the Natural History, to image the specimen, the calcified specimen, or kind of like, it looks like a very small stone, and we've been able actually to visualize the structures within this calcified structure or specimen. And for this, you require actually a very high energy just to pass through the specimen. So that's why the energy. So the energy is probably the overkill for a little mouse, but those scanners are kind of universal. It's not only for in vivo imaging, but also for specimen imaging, right? And then, so if you have this micro CT scan shown over here on the right side, so really just to improve the quality of this image, so you need to apply a lot of processing. And we've been able actually to apply those processing using the advanced workstation and show actually the images, which is on the lower part of the screen, where you actually remove all the artifacts from the image and focus only on the vascular tree in the mouse. So this was probably the best, one of the best images that I acquired in my life, using a very small object like a mouse, which was injected with a contrast agent, and then create actually those spectacular images where you can really look at the vascular branches. You can do some quantification of the, so we applied actually another algorithms to look at the diameter kind of histogram. So trying to find out what is the diameter of the different vessels on this image, and how, for example, a therapy or physical exercise changes this. So it was a really great study, but acquired, acquisition take, like 4 hours per specimen, and then processing was also a multi-hour processing time. But similarly, so we've been doing with the same technique, with the same methodology, the vascular cast of the mouse legs. So on the left side, so you got the reconstructed image from the specimen scanner. Again, this was the leg of the mouse. Maybe you can recognize the bone structures here and some vessels combined together. It was placed actually in some like a tube just to avoid any movement of this vessel during the 4-hour scanning. But really, for me, it was nothing which I would consider a good quality image. But again, application of those high-end processing workstations allowed us actually to create those images, which on the right side you can have the segmented bone in the white, and then the red, it will be a vascular tree with the resolution. So the smallest vessels that you can see over here, so they are within 25 microns. Again, a very nice example of the imaging. And finally, so this is a future technology. I just wanted to tell you a little bit about the multispectral CT. So I learned about this a couple years ago, and partially is because of the development of the new detectors. So far, all the technology which I showed you, even the dual energy or multi-energy CT uses the same type of detectors, right? So which detect the ionizing radiation. So for example, the X-rays. However, probably some of you recognize what is the CERN, or the Large Hadron Collimator. So this is the kind of accelerator which has the length of the 27 kilometers. It's located close to Geneva in Switzerland. And it allows actually to accelerate particles and then collide the beams of those particles together at the energy scale that it was never tried before, right? So those studies are done in CERN. So this is the European agency. Why I'm showing this, because for this particular studies, when you have high energy beams which collide together and they produce thousands of different type of particles of different mass, of different polarity, and so on, you require a very specific detector. And those detectors, so this is the part of the visualization of the event when two beams actually they collide together and they produce this, thousands of millions events or particles which are emitted at the same time. So you need to have a very sophisticated detector system actually to acquire that. And one of those detectors, which are based actually on the MEDIPIX technology, which was used by CERN, or it's being used by CERN. It's considered to be the most advanced chip, like a detection chip today, which is capable of detecting each individual particle hitting a pixel, which was never tried before or never experienced before. So always there was like an averaging of multiple pixels hitting or multiple particles hitting the detector. In this case, it allows a very accurate energy resolution. Different energy levels are translated visually into different colors. So this is actually what MEDIPIX technology does. And one of the companies, the Mars Spectral or Mars Bioimaging company, I think located in New Zealand or Australia. So they produced a system, a prototype system, which uses those type of detectors, and it's called Mars Spectral CT. And those scanners, they generate a multi-energy images with a high spatial resolution and low noise. So, so this allows actually for a simultaneous identification with a very good quality of soft tissue, bones, cartilage, and also some agents, contrast agents, nanoparticles, and pharmaceuticals just in single scan. So what it means that it kind of shoots, different type of energies. So not single energy or like a fraction of the energy, but kind of like a list mode. So this is called like a list mode or continuous emission at different energies. And this type of detector, which is implanted or installed in the system, can actually differentiate those different energies or collect them. So I think you are waiting for the images. So these are the example of the images. So this is a part of the human leg, which was acquired with this technology. So it allows for the very good, actually very high resolution, but also very good determination of what is the tissue, soft tissue. So I can tell you that with a regular, for example, CT, it will be not possible to differentiate. Of course, we can differentiate the bone from the tissue, but definitely not the type of the tissues, right? So these are two different type of the tissues. I don't remember if this was like a fat tissue and this was kind of like a muscle, but using this MEDIPIX technology or this multispectral imaging is actually possible to differentiate those using the single scan. This is another example from the patient who was wearing a wristwatch. But again, you can observe that this is a metallic surface, right? So it will be highly attenuating. In the regular scan, CT scan, it will create a lot of artifacts, so-called starred artifacts, because of this very high attenuation of the metallic pieces. But using this actually system, it's completely fine actually to image some metallic parts together with the bones and the tissues. So I think these are all images that I have. So So this is the kind of a conclusion of our discussion using the CT imaging. You will see in the future, so actually in the couple of weeks, when we'll be talking about some other imaging modalities, that in many cases, the CT is used in combination with other modalities, right? So, so you will see that when we'll be talking about the PET imaging, so during the application discussion, so when we'll talk about the application of the nuclear imaging, so very often those PET or SPECT systems will be combined with the CT, because CT always provides the information about the anatomy. Unfortunately, the PET or SPECT images, so they are difficult to interpret without anatomical information. But we'll talk about this. So that's actually concludes our CT imaging. And I think we got still 20 minutes time or 15, 20 minutes time. So it's a good time to start the next modality, which will be a PET imaging. So we'll talk about the nuclear imaging, the first one, which uses the positrons and annihilation energy to acquire the images, which is called the PET positron emission PET positron emission tomography. Are there any questions about this part? We can always go back actually to the CT imaging when we'll be talking about the homework on Thursday. So question is from Elizabeth. Would high energy cause an increased risk of harm to patient or mice? Yes, so that's a good question. So high energy in general will cause the increased risk to patients. In terms of mice or generally experimental animals, it's not so clear. So definitely it may cause some harm, but it will be kind of like a long-term harm. So if we are talking about the effects of ionizing radiation, the high energy ionizing radiation, so we are talking about years, for example, in the future, right, in the lifetime. So the typical mouse will live about 2 years, so probably you will not see those effects seen in the animals. But in the patients, yes, the higher energy will cause the increased risk to harm. I wouldn't say harm, but it may produce some undesired effects long term. So therefore, the new technology, or if you are, for example, monitoring what new scanners, CT scanners are manufactured by the companies, it's one of the new kind of directions is to reduce the exposure. Reducing exposure means that the time to acquire should be reduced, and also the energy or like a density of the energy should be also reduced. Another question is, do they have to adjust the energy for patients of different weights? I don't know about this. So never had actually this example that if you have a very obese patient, so you need to increase the energy. It's not the case. Of course, the quality of the images will be reduced because of the higher attenuation. So the X-rays, they pass through much larger or higher distance, right, through the patient of the obese, for example, patient. But I don't think that it's good actually to increase the energy because of this harmful effects. Like an obese patient versus a child or someone small. So again, I don't think that that in the clinical systems you are increasing or decreasing the energy based on the weight. No, so these are kind of like a predefined the energies of the X-rays which are used in the clinics. From Harpal, there is a question. It shouldn't because of the penetrating power of the radiation. Yes, I think you're right. Okay, so let me just stop sharing this. So if there are no more questions about this, so let's spend the last 10 minutes on the introduction to the PET imaging. Probably you will not see too much of the introduction because I have actually our favorite part, which is, hold on. which is the illusion of a day. Okay, but before we'll start this, talking about the PET and what it is generally and how we detect this. So, so let's have a look at this type of illusion. So what I wanted to do, so you see kind of like a pattern which changes over time. So just look at the kind of the crosshair in the middle of the screen for a couple, maybe 30 seconds. And when you are kind of concentrating on this, after some time, you will see that there is actually a green kind of like a circle going around, right? If you are not changing the kind of the position of your face after some time, instead of the pink kind of color, you start seeing the green ball going around. I hope that you can see that. Let me see. Yeah, so Aaron say, I see it. That's good. So at least you've seen this. I've seen this too. But of course it needs to rotate. So why is that? Again, it only works where you are focusing on the crosshair. But if you are, for example, moving your sight and looking, for example, where is this green ball? So then you will see that it's actually no green ball there or circle. So why is that? Well, it's actually associated with something that you are comparing to the surrounding colors. So for example, here, and if you are comparing to the surrounding colors, so very often the human eye can find the incorrect interpretation of the color. So for example, here on the screen on the right side, so you can see this kind of like a checkboard, checkboard with some cylinder, which gives the shadow. Well, if I will tell you that this part, so the A, has the same color as part B, probably you will not believe me, right? Completely at all. But it's a true thing. So I can provide you with some or you can test it yourself using the imaging processing system. That actually these are two colors, exactly the same color. So A and B are exactly the same colors, but why B looks actually whiter? Because it's actually compared to the shadow right around over here. So the shadow which gives the cylinder. So and it's again very important for imaging, right? So because you are analyzing the images. So if you are an operator and looking at the medical images, so very often you can find out that something is brighter, and in reality maybe it's not. Maybe there is some other kind of like a shadow, which is, for example, in CT images, very often coming from the skin. So I got another kind of like illusions later in the semester when you will see that if there is like an older man with kind of like very, I'd say, flexible skin, and there is an image, actually the CT image, which shows that when this kind of skin flaps, it actually creates an artificial shadow on the CT image. So this could be an example like this. All right, so so this is actually we start talking about detection of the results of the radioactive or products of radioactive decay. And this is kind of like an anecdotal story where is this electron, there is a gamma particle, and the electron is saying to the gamma particle, why would you ignore the guy who just walked past? And the gamma says, well, I do not interact with other protons. I'm sorry, other photons. And it's true. So there is no interaction between the photons, but there is interaction between other particles. And the radioactive decay is associated with the fact that we got a different kind of like attraction and different forces within the nucleus of the atom. So because the nucleus consists of protons and neutrons, and they are bound actually together by strong interaction, so-called strong interaction. But we have also other interactions between the kind of attractive force of the strong interaction, but there is also a repulsive force of the electrostatic force between the protons, right? So if the protons are together, so of course, because they are positively charged, so they kind of experience this repulsive force of electromagnetic force, right? I'm sorry, electrostatic force. But between the protons and neutrons, this is the strong interaction. So they kind of, so this actually, those two processes, they keep the nucleus together. But now we can imagine that if there is too many protons or too many neutrons, so it can happen that actually the nucleus, it's unstable. And instability, it means that it will kind of like need to relax, which means that it needs to produce another particle or change the number of protons and neutrons to make it again kind of more stable. And this is the kind of like a rationale for a radioactive decay. And we know several of those decays are existing. We talk about this during the first week of our classes. So, and because we are starting talking about the PET imaging, so where the PET imaging kind of, it's better than the other modalities. Well, we just finished talking about the X-ray CT, right? Which is considered as an anatomical imaging modality. It's very good to image anatomy, very good to image, for example, changes in anatomy. So a movement, or for example, some changes in like a growth of something, like a tumor growth. So it's a good technique to use. However, on the other hand, the PET imaging is considered as a functional imaging modality, which talks more about the function, looking at the molecular events. So, for example, a molecular events like a changes or kind of like a receptor density or receptor expression, also metabolism, like a glucose metabolism, also some physiology can be very well assessed using PET imaging. So this is where PET imaging has the application, definitely not the anatomy. So when we talk about the radioactive decay, and we got a couple more minutes. So we talk about the alpha decay. So with the alpha decay, which is not used for imaging, it's when the nucleus splits by emission of alpha particle. So alpha particle is relatively heavy. It contains 2 neutrons and 2 protons as a single particle. So one of the examples is the uranium, so uranium-238. It's being converted or decays to thorium-234 with the emission of alpha particles, and alpha particle is actually something which it's kind of has interesting features because it's very easily to be blocked, right? So even the piece of paper will block the emission or the penetration of the alpha particle. So so that's why if you place an alpha emitter on your skin, so it will not penetrate through the skin. So therefore, you may say that, well, it's safe, right? Because the alpha particles are very easy to block by, you know, even piece of paper or the layer of the dead skin on the surface of your body. So probably it doesn't cause any problems. Well, in fact, the problem is when it's being digested. So if the alpha emitters are digested, so they cause actually a kind of a lot of problems inside the body, because the inside the body, so they are exposed organs and they are affected by the alpha particles. And I call it actually the alpha emitter, which is one of the isotopes used as the alpha emitter is polonium. I call it also the radioisotope of political controversy, and there's a story behind that. So polonium was actually discovered by Pierre and Marie Curie. And maybe some of you don't know about Marie Curie. So he was a Polish origin. So she was Polish and studied in Sorbonne in Paris when they met with Pierre Curie. And when she discovered actually a new element, so she actually called polonium because of her home country, Poland. But the polonium, in the addition to being the alpha emitter, It has actually a half-life, the polonium has half-life of 138 days. It's alpha emitter, but it's actually very poisonous. So there are several of the known very well and described poisoning cases. One, it was the Irene Joliot-Curie. So she was a daughter of Marie Curie. She was poisoned because of the alpha emission by polonium. But the other one was more kind of political controversy. So Alexander Litvinenko, so he was, so he died in 2006, and he was actually poisoned by the Russian secret agents. So he was a dissident residing in Great Britain, in England, and he actually died of the exposure. So this is actually Litvinenko. He actually drank tea, which was poisoned or with the added polonium, and a couple months later, so he died of the problems associated with the radioactive decay of the polonium and alpha particle actions. So sad story, but true. But it tells you that actually alpha emitters or alpha particles, they are very, very dangerous. I think this is a good time actually to stop. So we will start talking about some other type of radioactive decay next time, which will be used for imaging, especially for the PET imaging. So this will be the unstable atoms, which they just to reach the stability, and so they need to emit a positron, and that's where the name for the PET imaging comes from. It's from the radioisotopes which emit the positrons, which will be then follow kind of like an annihilation process with the electron, and the emitting and the resulting energy will be collected by or detected by PET detectors to create an image. But we'll talk about this on Thursday. So and also on Thursday, if we will have time, so we can start talking about the homework number 1. All right, so thank you very much for your attention today, and I wish you a good rest of the day, and we'll see each other on Thursday this week. So thank you.
Oh, sorry, Dr. Dabrowski, are we talking about the homework on Thursday?
Yeah, we'll talk about the homework on Thursday, and also on Thursday I will release actually the homework on the Moodle. So if you cannot, for example, be on Thursday, it should be fine, because the homework will be self-explanatory, and I will also attach the video kind of to explain the homework.
Okay, thank you.
You're welcome.
I also wanted to ask for clarification. When we were talking about contrast agents, I thought that we would want a lower attenuation than a higher one. So I just was wondering what would be ideal for the best CT images regarding attenuation and energy.
Yeah, we want actually to increase the contrast on the image, right? So for example, if you are doing the CT imaging of a lung, right? So for example, the lungs, because it's a very low attenuation, so the X-rays, they pass through the lungs almost without losing the energy, right? So therefore, just to, so if you are interested in imaging, let's say vessels, right? Or for example, tumors, but most contrast agents are actually used for vessel imaging. So you want actually to increase the contrast agent, to increase the contrast on the image by increasing the attenuation. So actually more CTs will be attenuated, so they will result in kind of like a more bright image on the CT screen.
Okay, that makes sense. And
Okay.
then what about for energy?
In terms of the energy, so it's not very clear. So again, it depends also on the application, because if you are imaging, typically the CT scanners, they are set and at the kind of like a nominal energy. So in my scanner in the lab, so we set at 80 kilovolts, and we are using this for the last 10 years. So we didn't change any energy because it was perfectly fine to image any objects that or animals and also specimens. But one case that I mentioned today in the class was the specimens which were kind of like calcified specimens, right, from the Natural History Museum. And in this case, we had actually used another scanner, which allowed us actually to increase the energy, the penetration energy.
Okay, thanks. That makes sense.
All right.
Thank you so much. Have a great day.
Thank you for the question, you too.